So continuing on with looking at basic analysis of time series data, let's say that we wanted to find the mean of each of the variables in our data set. Well, that's very easy. Simply use the mean function applied to the data frame. So df, our data frame dot mean, and it's a function, hence the brackets. Now there are probably a number of options perhaps you could set here, but this will do fine. Now this of course is going to take the mean of every variable. If you just wanted specific ones, of course, then of course you would indicate those after the df in the normal way, particular columns you wanted. But if we want all of them, then there we are, very easy. Again, of course, you could put this into its own variable if you wanted to. Now, this we can easily plot these means in a bar chart. So I've done that here. This is all very familiar. We've seen how to use plot.bar and the title and ylabel functions. One thing I don't think I've shown here before is this option here in plot.bar, where you can set the width of the bars. If you don't include that, it'll use a default width, and when I did this without this width option, I thought the bars were a little bit too thin. There was too much of a gap between the individual bars, so I've put this option in here. Again, this is a bit of trial and error. You have to try different values to see which looks right, but I thought 0.8 looked okay, and there we are. So obviously if you put 0.7, they'd be a bit thinner, 0.9 a bit wider. I wonder if I haven't tried this, I wonder if you put width equal 1, that would actually eliminate the gap. I'm not sure, but I think that looks very nice. Of course, it's in the ggplot style because of the option I set at the beginning. Here I haven't bothered to rotate the x-axis labels because they actually look better like this. I think if they were rotated, they would be scrunched up, although presumably you could reduce the font size, but I think that looks fine. Now, one chart that I haven't looked at before is a scatter graph, which of course is a common type of chart that you might want to plot if you're looking at the relationship between the two variables. Again, this is very easy. There's an option, plot.scatter, just like we had plot.bar here. Remember, if you just put plot on its own, it does a line graph by default. So here, what you do is you use plot.scatter on the data frame, and then in brackets you indicate which variable that's in your data frame you want on the horizontal axis, x equals, which one on the vertical axis, y equals. And that's pretty much all you need if you want to keep with the defaults, but you can actually set the color of the points and the size with this S option. You could make them slightly transparent with the alpha. And also, if you don't like the default marker, you can set that with the marker option. You can find information about these various options in the help file or on the page on Pandas page that I've looked at. No, I think it would be the Matplot page, wouldn't it? The Matplot website for this, of course. And then a title and to show the graph. So let's see what we get here. So we got a nice looking scatter graph here. Actually, I've set the marker to be an X. I've set the color to be green. It's slightly transparent. The size is, I think, just about okay. Not too big, not too small. Again, there's a bit of trial and error here to see what looks good. Notice I didn't put the lock equals left here option, which I have here. So that's why we're getting a centered title in this case. I notice I didn't need to set X labels and Y labels because it used the names of the variables, so that looks fine. Obviously, if they are not appropriate, then you can set the labels as we've done before. So that's a nice scatter chart. Now, what about transforming your data? What about doing creating some variables which are transformations? Well, one thing that you might want to do often with time series data in particular, but this could apply to cross-section, is to create an index number series of your data with some given base. If, for example, we were wanting to compare the change in the debt to GDP ratios of these various countries, a chart like this doesn't really tell us which ones have increased the most relative to the others, because they're all starting from different points here. And the way you often overcome that is, of course, to turn these variables into a corresponding index number series with a common base of 100, and then they will all be starting from the same value, from 100. You can see how they compare. So how would you do that here? Well, we can use this transform function, which I've looked at before, which takes what's called an anonymous function, a lambda function, and if you remember the syntax from this from a previous video, you simply put lambda and then some variable name x is perfectly fine, and then with a colon, then you give it some expression, some function of x to do what you want to happen, where x stands for each value in the variable. So what I'm doing here is I'm taking each value x, I'm dividing that by the value at the first index point, which would be the starting value here. Actually, this is not the starting one because this is a subset, if you remember. But so if we go back to we've got the full data set here, this starting one here. And then, of course, x stands for each value in each particular variable. This will work on all the variables. So, for example, with Germany, x will stand for this one, and then this one, and then this one, and it's dividing the value by the value of x of the variable in the first position, in the first row, hence the index notation there, which of course is how you, and then times it by 100 to give an index number, which of course how you create an index number series. You choose one value as the base, and then you divide each other value by that base figure and times by 100. So that's what this is doing here. If you look at what I put in here, remember x simply stands for each value in a series, and since I'm doing this transformation on the entire data frame, this function will apply to each series: Germany, France, Italy, and so on. So x means take each value in a particular variable, divide that value by the first value. So I've used the index notation there we saw before to choose that particular first row, and then I'm times by 100. So this should do exactly what I want. It should, and I'm storing this in a new data frame, and that should contain index numbers series for each variable. Okay, so I need to now display it. I'll just look at the first 5. And there we are. You can see it's done exactly what I wanted. For each variable, it has taken each value, divided it by the base value and times by 100. So those are that was the base, of course, and then here are the rest. So hopefully you can see how you can do that. Okay, so now I'm going to plot these index numbers, but without Ireland, because that's a bit of an outlier. So I'm just excluding that. So we've seen how to use this drop function before to only to drop certain variables from what you're trying to plot or from your data frame. Okay, so as you can see, we've got another line graph here, but this time, because these are index numbers and they're all starting from 100, you can see much more clearly which ones have risen the most relative to the others and relative to the starting value here in quarter 3, isn't it? Sorry, quarter 1, of course, 2006, yeah. Another thing that you often want to calculate with time series data is the growth rate from period to period. Now again, you can do this with using the transform function and by putting in some function here to do it. So again, remember, x simply stands for each value in a variable. So it says it effectively does a loop through. It loops through each value in the data set in each particular column and applies this relationship. So it takes the first value and subtracts from that the previous one. This is the function in pandas to do a lag, to lag a variable, to look at the value 1 period back or 2 period backs. In R, I believe the function is called lag, if I remember correctly. Here it's called shift. So what this is doing is finding the first difference here. It's finding the difference between the current value and what it was 1 period back, and then it's dividing that by the 1 period back value. So as you can see, this is finding the proportionate change and then times by 100 to give a percentage change. So this is finding the percentage change as the variable changes. And that, of course, is how you would do it, isn't it? You'd find the change, the actual change from the current value to the one period back, and then you divide it by what it was to start with, 1 period back, and times by 100. And again, this will loop through every value here. I'm doing this on the actual index number series, but you could have used, of course, the actual values. Either will do, and it worked its way down each column, applying this function. So let's look at that, and there we should get what we want here. Notice, of course, the first one will be missing because it can't work that out because there's no previous value for it to use here. So the first one, of course, will be in the second period. That will be the percent. So this value here is the percentage change from here to here, and then this one is the percentage change from here to here, and so on. So hopefully again you can see how to use the transform function here with an appropriate expression here to do exactly what you want. And notice it's very neat, this, because you don't have to write your own loop to loop through each column in turn and each value in turn. This does it automatically by simply allowing x to stand for each value. So it works down each column, then onto the next column, and onto the next column. Okay, just a couple of other final things here. Again, something you might often want to do with time series data is to take the log, the natural log of the data, because that can often be a useful way of plotting time series, particularly if you've got a variable which is tending to grow exponentially over time, tending to grow by a certain percentage on average from period to period, such as say GDP. It's often useful to plot the natural log of that because the slope of the log graph tells you the average growth rate. So how do we find the log? Well, here you use a function in NumPy, hence the NP, called log. and this will find the natural log. If you want the log to base 10, then it's a different function. I can't remember what it is, but you can look it up. But with time series data, you typically want to take the natural log, the log to base e, which is simply log here. So as you can see here, I'm applying this function. Notice a slightly different syntax here. It's not a dot function. It's not df dot np.log. It's np.log and then in brackets df to find the log. And then I'm storing that in this variable. And then I'm just going to show the first 10, isn't it, by default, if I just put head without any number in the brackets. Sorry, 5. First 5 values it gives you by default. And there we go. That's taken the log of every value in my data set, my data frame. And finally, let's look at another reason why you sometimes want to take logs. Particularly this is true if you're doing regression analysis, econometrics, that side of stuff with time series data. You can an approximation to the growth rate from period to period, which we calculated, here was the growth rates. Here I calculated them exactly by using the formula to calculate a growth rate. But you can often simply find the difference in the log values, because that will also tell you the growth rate. It's an approximation. It's not, these are exact, but an approximate growth rate is the first difference of the logs, the difference in the log value from period to period. If you've done this sort of thing, you'll know what I mean. It's not exact, but if the growth rates are particularly small, like these ones here, it turns out to be virtually the same. It's quite a common procedure in econometrics, in other work like that. So what I've done here is I've taken the I've got my log variable here, remember, log underscore df. So to find log growth, I'm simply finding the difference between the current value and what it was one period back. Notice I'm using that lag operator again here, shift, to find one period back. So that should find the first, and again it will work through the whole data set column to column, so it will do this one and then this one. So notice you don't have to tell it, there's no writing loops here or anything. It's very easy. Simply tell it what you want to do to find the difference between the log value and the log value one period back. That's all you need to do. I'm storing that in a variable log growth, and there we have it. Very, very easy. If you've used R before, or you'll know this is essentially what you would do in R, although the operator there I think is called shift, lag rather than shift, but it's just the same basic type syntax. And notice that these log differences here are very close. In fact, they're virtually identical to these actual growth rates, and that will be the case. If the actual growth rate is quite small, then this log approximation is certainly accurate enough. They're not quite the same. You see that one's quite slightly different, but there's really not much in it. Okay, so that completes looking at how to do some basic time series data analysis using Python.